So this first one, the geometric distribution. So the way we're going to motivate it is just by this problem. On average, how many times must we roll a fair die before we get a 6? So the idea is we're going to roll a die, then we're going to roll it again, and roll it again, and roll it again. And we're just going to keep rolling until a 6 appears. And the question is, on average, how many times must I do this before I will actually get a 6? Let's actually have a look at a demo. So I'm just going to build a simulated die roller. So here I've got roll dice, and it's just a function that returns a random choice, 1 through 6. So that's my simulated die roll. And then what I'm going to do is I'm just going to do a while loop, which continually rolls the die until a 6 appears. Once a 6 appears, then it'll just spit out the sequence of rolls that I got, and then also return how many rolls it took me to get that 6. So in other words, the length. So let's just execute this. Oh, there it took 18 rolls before I got a 6. So what we're interested in is the expected number of rolls that I would take to get a 6. This particular example, it took 18. Let's run this again. Now it took 10. Let's do it again. So each of these is an experiment. Now it took 5 rolls. So I do another experiment. 7 rolls. And I do another experiment. That one only took 1. I got it on the first thing. So I'm getting all, oh, again, I got it on the first one. We'll do a couple more here. Oh, that one took 6 rolls. And so the question is, I've done this experiment a bunch of times. What is the expected number of rolls that I would expect it to take in order to get a 6? Would I expect to roll the die 2 or 3 times? Would I expect to have to go up to 10 times? What is my expected number? That's what we want to calculate. We want to figure out what is the expected number of rolls. And so let's go ahead and see how we would actually calculate such a thing. To do this, I'm going to actually introduce a few random variables. The first random variable that I'm going to introduce is a random variable that just returns the value at a particular location in my die rolling sequence. So the way I'm thinking about this is I've got a sample space. What is my sample space? It's just the collection of all the possible infinitely many die rolls I could do. Now you might say, well, why infinitely many? Well, the idea is I want to be general in how I approach this problem. Here I'm interested in how many times I have to roll the die before a 6 appears, but that's only going to come into play for my random variable. Underlying that is a sample space. What's my sample space? My sample space is just I continually roll a die. I roll it again, 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 and I get an infinitely long sequence of possible die rolls, and I get lots of possible, actually infinitely many long sequences of die rolls. All the possible ways. Imagine everyone on Earth rolling a die continually, forever, and generating different sequences. That's my sample space. So what I'm going to do is I'm going to create a random variable on that sample space. In fact, I'm going to create infinitely many of them. So I'm going to let Ri be the random variable which returns the value of the ith die roll. So what would that look like? For example, suppose I rolled a die and I got a 1, a 4, a 3, a 3, a 2, a 6, a 7, a 9, an 8, and so on. So that's my infinitely long sequence of die rolls. What Ri is doing is it's going to return the ith value. So for the particular case, let's say R5. Suppose I want to know what is R5 of this. Well, this is telling me look at the fifth die roll, so 1, 2, 3, 4, 5, and return the value. And that's going to be a 2. So that's what our random variables Ri are. They just return the value of a particular die roll. So now we could ask some questions about this. So for example, I will let P be the probability that the ith die roll is a 6. Because that's what I'm ultimately interested in. This is where I bring into the mix about rolling a 6 or not. So what is the probability of rolling a 6 on the ith die roll? Well, the idea is that when I roll the die and then roll it again and roll it again, those are all independent events. So the value on the ith roll is independent of any other roll. So what is the probability of getting a 6 when I roll the die for the ith time? That's just the probability of getting a 6 when I roll the die. The probability of getting a 6, assuming it's a fair die, and it is, because we say it there. So a fair die meaning all numbers are equally likely to occur. Then we get the probability is 1/6. The other thing we want to record is what is the probability of not getting a 6 on the ith roll? Well, the probability of not getting a 6, that's the complement of getting a 6, so this would be 1 minus P, or in other words, 1 minus 1/6, which is 5/6. Now you may say, why did I call these things P and Q? Why didn't I just use 1/6 and 5/6? Well, the idea is I'm going to try to be general. So I'm using an example to build up a general situation here, the geometric distribution in general. But I'm doing it through this particular example, so I'm going to identify what are the key aspects in this example that we want to focus on. And the two aspects are the probability of a 6 occurring on a particular roll. We'll consider that a success. So the probability that we have a success on the ith roll versus the probability we don't have a success on the ith roll. Okay, so we got those two probabilities. Now, what we are really interested in is how many rolls we have to do before we get a 6. So that's where we're going to introduce our main random variable we are interested in. So we'll let T be the random variable. So I won't say be the random variable, but it'll be the number of rolls made to get a 6. And so for example, again, we'll look at our example up above. Here we were doing 1, 4, 3, 3, 2. Oh, finally I got a 6 appearing. Now I'm going to include the remaining numbers, but when we're actually doing this in practice, we would stop at a 6. But here our sample space is all infinite sequences of die rolls. So what is T of this? Well, T would say, how many die rolls did it take to get a 6? So there's 1, 2, 3, 4, 5. Ah, there it is. You finally got it. Oh, and it just happened to be, in this case, happening on the 6th roll. So I finally got a 6, and I got it on the 6th roll. So the 6th roll gave me that 6. So that's the random variable we are really interested in, because that's the one we want to know what is the expected value for T. What is the expected value for the number of rolls in order to produce a 6? So this is what we're interested in. So to summarize where we are so far, we've got this random variable T on our sample space, and what it's producing is, in this case, it's producing an integer from 1 or more. So we'll just write this as Z, the set of integers, plus indicating that it's the positive integers, so from 1 onward. So I don't have to say it's producing a real number, because in fact in this case it's producing a positive integer. What is S in this case? This is all the infinite sequences of die rolls. All the sequences of die rolls that we can have. And for each one of them, we are just working out when the 6 first appears. Okay, and that's what we want to find the expected value of. Now, to find the expected value, what we are going to do is we're going to sum over the range of the random variable times the probability that we get that corresponding value in the range. Now, this is where it was important to note that our range is 1, 2, 3, 4, and it goes on forever. So our range is infinite in this case. So we'd like to know what is the probability that we take on a particular value in the range. So what is the probability, for example, that our random variable t is equal to 1? What is the probability that we are able to get a 6 on the first roll of the die? Well, that would be 1/6. What's the probability that we are able to get t equal to 2? So in other words, we get a 6 on the second roll of the die. Well, that means that we want R1 to not be 6, and we want R2 to be 6. Remember, Ri was just the value of the ith roll. So we want the value of the first die. We want the value on the first roll of the die to be not 6, and we want the value on the second one to be 6. Now this is an AND. This is, we'll make a note here, we are really looking at the probability of A and B, the intersection, and that is the probability of A times the probability of B if A and B are independent. And in this case, they are independent because the value on the first die roll is independent from the value that I'm going to roll on the second die roll. So those are independent. So this is the probability that I don't get a 6 on the first one times the probability that I do get a 6 on the second one. And what's the probability that I don't get a 6? That was Q. And the probability that I do get a 6 is P. And I just have to move this over a bit because what is that equal to? That's equal to 5/6 times 1/6. So there's our probability that t is equal to 2. And now that we've done those first two cases, we should be able to get into the flow now of what the remaining ones are. So what is the probability that t is equal to k? That I get a 6 on the kth roll of the die and no sooner. Well, this would be the probability that R1 is not 6 and R2 is not 6 and all the way down to RK minus 1 is not 6 and RK is 6. And so I need the first roll not to be a 6. That probability is 5/6 times 5/6, not a 6 on the second roll, times all the way down to 5/6. And then the last roll I want to, or the kth roll I want to be a 6, so the probability that will happen is 1/6. So in other words, it's 5/6 to the k minus 1 times 1/6. Or in terms of our p's and q's, this is q to the k minus 1 times p. And if I continue writing that here, this was p. And so I'm just going to draw your attention that this one was p, this one was qp, and in general it was q to the k minus 1 p, which meets the pattern that the first two have. All right, so now we've got these probabilities. So now we can go ahead and work out the expected value. So what is our expected value for the random variable t? It's the sum over all of the k's in the range of our random variable. Here I've called my random variable capital T. I'll make that a little bit cleaner. And so we are taking k times the probability that t is equal to k. This is equal to the sum as k goes from 1 to infinity of k times q to the k minus 1 times p. Oh, but there's a p in all those terms, so I can bring that p out front. And I get this expression here. So there's my expected value for t. It's p times the sum of k equals 1 to infinity of k times q to the k minus 1. And now our question is, what is that? Can I find a simplified version of what that sum actually is? And the answer is yes. We can work out the value of this sum. So we'll say, what is the sum? So we'll write it out. This sum is k equals 1 to infinity of k times q to the k minus 1. What that is, the sigma notation is shorthand for this sum. It's 1 plus 2q plus 3q squared plus 4q cubed plus dot dot dot. So that's the sum we are interested in finding shorthand or a closed form for. So what is this? Let's call it something. I'm going to call this thing a of q. And so what I notice is that a of q, which I'll just write it out here again, 2q plus 3q squared plus 4q cubed plus dot dot dot. If I multiply that by q, then what I get is just all of a times q, so each one of them. So q times 1 is q. But instead of putting it right under the 1, I'm going to shift it over. And then what's q times 2q? That's 2q squared. And then q times 3q squared is 3q cubed. And so on down the line. And so now what I notice is if I take the difference, in other words, I take a of q minus q times aq. What I get is 1 minus, well, there's nothing there, so I get a 1. And then I get a 2q minus a q, so that's a q. A 3q squared minus 2q squared, that's a q squared. 4q cubed minus 3q cubed, that's a q cubed. So I just get this. And that's a geometric series. And that geometric series sums to 1 over 1 minus q. And so I have a nice closed form for that expression. Now I notice that I can factor out the a cubed from each of these. So I get an a cubed times 1 minus q, and that's equal to 1 over 1 minus q, and therefore I'm able to solve for aq. It's 1 over 1 minus q all squared. And so there we go. We've managed to figure out what the value of that sum is. And so that means we can now fill it in. So this is now, I'll do it here, but then I'll also do it down below. This is now equal to p, so the whole thing is now equal to p times 1 over 1 minus q all squared. But remember, 1 minus q is p, because p was 1/6, q was 5/6, so 1 minus q is also 1/6, so that's a p. So really this is p times 1 over p squared, so it's p over p squared, or in other words, it's 1 over p. Again, I'll write it down below again, but I just wanted to cut to the chase here that we've now managed to figure out what the expected value of t is. It's 1 over p. P is 1/6, so 1 over 1/6 is 6, so we've worked out the expected value of t. It is 6. So I expect 6 die rolls to happen before I get a 6 appearing. We'll come back to that because I guarantee there's probably questions being asked about finding the value of this sum, this whole step that I put in red here, finding the value of that sum. So this is an infinite sum. We just wanted to work out what its value was. So the way we did it here was we used algebra. So we said consider the sum, and let's just call it AQ. So that's what we did here. Consider that sum, let's call it AQ, and let's just explore the properties that it has. Well, there it is written out. AQ is equal to that sum. If I multiply it by Q, I get almost the same sum. It's just each of the terms differ by, essentially the coefficients differ by 1. So that indicates to me that I should take their difference, because then I get a sum that I know the value of. It's a geometric series. So this is because it's a geometric series. Not surprising, the word geometric is appearing here when we are under the category of geometric distribution. So the geometric distribution, we're using the geometric series to get information about it. So that sum of 1 plus q squared plus q cubed and so on, that's 1 over 1 minus q. And therefore we use algebra to solve for AQ and get our result. Now for those of you familiar with Calculus 2, we could do a Calculus 2 approach to get the value of that sum. Now what would our Calculus 2 approach be? Again, we are interested in this series, the sum of kq to the k minus 1, k equals 1 to infinity, which I will write as 1 plus 2q plus 3q squared plus ... Now, we don't even need Calculus 2 per se here. All we really need is Calculus 1. You just need to know about a derivative. Do we know about derivatives? If we do, then we can notice that, hey, this looks like the derivative, in this case our variable is q, of the following. Q, I can even put a 1 in there, because the derivative of 1 is 0. The derivative of q is 1. What gave me a 2q? That would have been the derivative of q squared. What gives me a 3 cubed squared? That would just be a q cubed, and so on. So I could recognize that AQ is the derivative of the geometric series. Again, the geometric series is coming up. This is 1 over 1 minus q. So here I've used by geometric series, the sum of a geometric series. And in which case, when I take the derivative of that, I can use the quotient rule, or I can use the power rule. I can think of it as 1 minus q to the negative 1, in which case what I get is 1 over 1 minus q all squared. And so there's an alternate way to see how a of q is 1 over 1 minus q squared. Now this alternate way is for those who have seen calculus, Calculus 1, possibly Calculus 2 where you've dealt with series. If you haven't done that, no worries, that's why I did the first proof. The first derivation of what that sum is used just algebra. It was just simply an algebraic argument to get the value of that sum. So however it shakes out, we end up getting, and here's where I was going to write down the conclusion, so we end up getting E of t is equal to, and I'll write down that last result, P times the sum of that series, 1 over 1 minus q all squared, but 1 over 1 minus q, that becomes a 1 over p squared, which becomes a 1 over p. And in our particular case, p is 1/6. So since p is 1/6, we get a value of 6. So therefore, we expect 6 rolls before a 6 appears. So in other words, we expect to have to roll the die 6 times before we get a 6. We may get lucky, get it earlier. We may get unlucky and get it later. But on average, we expect to roll the die 6 times before a 6 appears. In particular, this is an example of what we call a geometric distribution. And we say that a random variable t is geometrically distributed with parameter p. That's why I use p above. P was basically our probability on any given roll, the probability we get a success. That is a 6 in this case was what we call the success. So that was 1/6. But in general, we say a random variable is geometrically distributed with parameter p when the probability of that random variable taking on the value k is p times 1 minus p to the k minus 1. And that's what we had in this case. 1 minus p was our q. So we had written this as q to the k minus 1 times p. But it could also be written as that, where q was equal to 1 minus p. And we've also worked out what the expected value is. The expected value of the random variable t is 1 over p. Now, we call this a geometric distribution because these probabilities are the terms of a geometric series, or a geometric, I'll call it a sequence in this case. Geometric sequence. So what is a geometric sequence? It's one in which the ratio of successive terms is equal to some constant. In this case, that constant is q. Or in other words, to get the next term in the sequence, you just multiply the previous one by q, and you keep going. Previous one times q, previous one times q, and you keep generating the next terms in the sequence. That's what a geometric sequence is. And so in this case, the probability distribution forms a geometric sequence, so we call the probability distribution a geometric distribution, or we say that t is geometrically distributed. Now, we've done the calculations. We see that we expect to get 6 die rolls before a 6 appears. Let's go back to our simulation and see if we get that. So we're now back to our simulation where, here in the first block, if I just keep executing it, oh, I get 1 die roll again. Here I do it again, I get 2 die rolls. Oh, those are pretty good. Then I roll it again, I get 8. So sometimes I'm below 6, sometimes I'm above 6. What this is saying, the expected value is, on average, how many I expect to get. So what that means is, what I should do is I should try this like 1,000 times, and then average the number of rolls I get. And that's what I'm doing down here. I'm just going to do the same thing, but I'm just going to average these numbers. So for each roll, I'm going to collect a list together. So I got an 8, and then if I use the previous 2 numbers, they were 2 and a couple of 1s. I form a list of all of those possible die rolls, or numbers of die rolls before a 6 appears, and then I average them. And so I'll just execute this block, and then we'll do 10 trials. So I do 10 sequences until a 6 appears, and I average the lengths of those sequences. And I get 5.9. And I do it again. And I get 4.3. And I do it again. And I get 5.5. The idea is that on average we expect it to take 6. So that means if I bump up my number of trials, I would expect this value to come out closer to 6. And it seems to be the case now. 6.0, 6.07, 6.097. So that means I've done 1,000 different trials. I roll the die until a 6 appears. I record the number. I do it again, record the number. Do it again, record the number. And I do that 1,000 times and then average those 1,000 numbers. And I get something close to 6. I can keep going. I can say, what if I did it 10,000 times? Now I'm getting something that's even closer to 6. Sometimes it goes away, but on average, we're pretty close to 6. I can do it 100,000 times, for example. And I get something that's really close to 6. So this is the experimental evidence that our theory is capturing what we want it to capture. So theoretically, we expect on average to get 6 rolls before a 6 appears. And there's some experimental evidence that shows that this is the case. All right, so let's have a look at the next distribution. So that was the geometric distribution, motivated through that example of continually rolling until some success happens. This next distribution, the binomial distribution, this we take a different problem.